at least I believe I basically now have a resolution to my obsession about how to make sense quantum mechanically of a perfect fluid. Okay, very much like you can make sense quantum mechanically of an harmonic oscillator or of the hydrogen atom. Okay, and very much like for the hydrogen atom, you find that some things change dramatically. Like the hydrogen atom, you don't have essentially a meaningful ground state. Classically, things fall into the, well, the ground state is UV dependent, and while quantum mechanically not, because there's no phase space to get in the on the nucleus. Okay, essentially levels are quantized and there's nothing there. Okay, and here I think it's going to be similar. Okay, so just here is just what is this noise? There is a noise. Oh, noise is slack. Let me turn off slack. Okay. Okay. So these are the people I've collaborated with on related stuff starting in 2005. But the work I will be talking today is mostly associated with work that was done with these people. There was first attempt 5-6 years ago, which did not go into a paper because we essentially started bickering on the meaning of what we were doing. And I believe that in recent work, we have finalized what to a large extent was already in here. And of course, this is where essentially the issue was stated. So there are many ways I could start this talk, but this is maybe the quickest, okay? So we are familiar as physicists with fluids. Fluids are ubiquitous, okay? There are many different substances, many different types, in many different regimes, hot, cold, systems behave like fluids. However, one thing is invariably true, is that if you take a fluid as some system, some effective description of a system, and then you go to, if you take a fluid and then you go to zero temperature, invariably this will no longer behave like an ordinary fluid. And there are many things that can happen at zero temperature. It can become a solid, can become a superfluid. There can be other more exotic states of matter, like Fermi liquids, but apparently none of them truly belongs like an ordinary fluid, that is to say like water, endowed with compressional waves and these very soft vorticose modes, where at the center you don't have a singularity, okay? Unlike in superfluids. Superfluid, you have vortices, but there's a singularity in the middle. In water, there isn't, okay? Now, this result that fluids are not there at zero temperature, I mean, in several cases, you can assess it directly by study, because the systems are weakly coupled. However, whether this fact is a general rule, even at strong coupling, at least to me, it is not clear, okay? And I think it is worth exploring. I mean, it may well be, I mean, one possible interpretation of this is that if you look at it carefully, it turns out that a perfect fluid quantum mechanically does not make sense as a system, okay? There's no such thing as a quantum mechanical perfect fluid. That's one option. Another option is that it does exist, but near its vacuum, near its ground state, it doesn't look nearly closely, not even closely to an ordinary fluid. I mean, you have to ask the right question to see that this is a perfect fluid, but in the quantum regime, okay? So this would amount to this, okay? So now, so how to address this question? Well, one way, I mean, I think this question can be addressed in a general form. In other words, our understanding of extended system theories is that you can infer their consistency to a large extent by studying their long distance dynamics, which is by using effective field theory, okay? I mean, to a great extent, okay? There are things that, there are additional constraints on effective field theories, but this is not what I would like to talk about today, okay? So I'm gonna think of the universality class of fluids. Okay, I'm imagining fluids can exist as a result of many microscopic systems, and I'm trying to see whether the idea, the universal Platonic idea of a system that is in the universality class in the IR as a fluid makes sense. Now, to do that, the crucial remark is the following. To start this analysis, the crucial remark is the following. Okay, what we're studying here is systems at finite density. System at finite density, and let's think for simplicity that these are systems that in their, call it ground state, they are homogeneous and isotropic, just to simplify the discussion. And so okay, these are systems that are homogeneous and isotropic. However, if you move into them, you realize that there is a preferential frame. So these systems, while even if they're microphysics, in fact, if the whole physics is relativistically invariant, and they have the conservation laws of relativity, like a conserved energy momentum tensor, a symmetric energy momentum tensor, yet the state where they are, over which you compute fluctuations, they are not invariant under the global transformations, meaning that the part of the space-time symmetry group, in particular boosts, are not linearly realized in this system. In fact, you can take this as a general trademark of finite density system. In other words, you can view all finite density systems as systems whose effective long distance description is in terms of a field theory with no linearly realized space-time symmetry. Okay, so you can now think in this perspective of a finite density system or condensed matter system. Group theoretically has instances of various instances, various universality class of how you break space-time symmetry. Okay? Depending on how you do it, then you construct the long distance description using Goldstone theorem. Okay, because when you break symmetry, long distance description has necessarily the Goldstone excitations, which in this case are the hydrodynamic modes, and then you can classify them. Okay? And let me give you an example of that. Okay, the simplest example of this is provided by the notion of superfluid. So what is a superfluid? Well, you can view a superfluid as a field theory where you have a scalar field, phi, and the scalar field takes real value, is endowed with a shift symmetry. In other words, phi and phi plus constant is indistinguishable. In other words, there's a symmetry, there's a shift symmetry in the field space. And a superfluid is a physical situation where this field can be used as a clock. Okay, in other words, where this field has a background, where for each value of the field there is a certain time. Okay, in other words, the field depends linearly on time. Now, a field like this with a shift symmetry always has a solution like that. Okay, because it is itself a Goldstone boson of some internal symmetry. So this solution always exists. And the superfluid corresponds to expanding around this solution. So in other words, you take your field, you take this solution and you expand fluctuations around it, okay? So in other words, you have a background that can be used as a clock. In other words, it intertwines the field and time. Now, the fact that the background depends on time tells you that time as a symmetry is spontaneously broken because your background transforms under time translations. On the other hand, the time translation is equivalent to a shift in phi, which is itself a symmetry. So there's a linear combination of time translations, ordinary time translations, and shifts in the field that is still unbroken, and it acts as an effective time translation. It is, if you want, is the time translation isometry, which is not just the ordinary one, the one that sits in Poincaré, but is a linear combination of that one and this internal shift. And the coefficients that raise this linear combination is nothing but the chemical potential. Okay? So I give you a superfluid as a system that realizes the following symmetry breaking. Poincaré times a U1 internal symmetry broken down to the Euclidean group of a homogeneous isotropic condensed matter system times an effective time translation. And in view of that, then to write the most general Lagrangian for such a universality class, you write the most general Lorentz Poincaré invariant Lagrangian for a derivatively coupled scalar expanded around this solution. And for instance, at the lowest order, the derivative expansion, the Lagrangian is controlled by just one function of this invariant, okay? And this function itself gives you the equation of state that relates the charge density to the energy density. And not only that, but when you expand it in pi, it will also relate precisely this equation of state to all the scattering amplitude with an arbitrary number of phonons. Okay? That's the beauty of, if you want, like chiral Lagrangian for pions, okay? Symmetry, when they're nonlinearly realized, they control not only the spectrum, but also how the way the long distance soft modes interact with one another. In the very same way, you can generalize, you can consider a solid, okay? Where a solid is based on the same idea as for the superfluid, where instead of a clock, you have a ruler, okay? And the ruler here, you want a ruler for the whole space, so you need 3 fields, okay? You need 3 fields, phi1, phi2, phi3. And these 3 fields, very much like before, have an internal translation symmetry in each of their direction. And so they are themselves Goldstone bosons. And they are expanded around the solution where they can be, each field can be viewed as a measure of space. In other words, before we had a clock, and now we have a ruler, okay? To each point in space, there's a unique value of phi1, phi2, phi3, okay? So they provide a system of coordinates, okay? Their own system of coordinates. And again, you can expand it, you can expand this solution around the solution, and you have 3 excitations, which are nothing but the 3 phonons of a solid. And then you can do the same thing. And then beside these shift symmetries, which corresponds to internal translation, which eventually we very much like translation in phi here and translation in time here, they're essential to recover space homogeneity in this solution, because even if the solution depends on space, there's a linear combination of ordinary translation and internal translation that is left unbroken on this solution. And then there's a question whether rotation is a symmetry or not. In normal solids, you only have some discrete rotations, but you could think of an ideal isotropic solid, a sort of jelly, where there is an additional internal rotational symmetry here. And again, the resulting unbroken symmetry is a linear combination of the two. In other words, a solid is a system where the Euclidean group of space-time within Poincare and an Euclidean group in an internal field space break down to the diagonal group. Very much like SU2 left plus SU3 right in QCD is broken down to SU3 isospin. Okay? And again, yes.
I have a question about this. So I understand that this is a good framework to derive the resulting effective action for solids, but if I see a solid, should I expect that the microscopic theory always contains this extra iso3 symmetry?
No.
In other words,
no.
In real life, I know that they do not have it because there are molecules.
You could break. You could
continuous.
So you could, as I said, I mean, if the solid, now we can get into the debate. I mean, we can get into debate about whether this symmetry I'm talking about here is continuous or discrete, right?
Yes.
Sure, but I think it's irrelevant. I mean, we can leave this discussion for later. I think for the moment, this is not important.
Okay.
But yeah, you could have, in particular, the rotational symmetry could be a discrete symmetry without any problem. Doesn't change what I'm saying. And yeah, I don't think there is any big deal here with if you have enough resolving power, I think you can even consider the case where internal shift symmetry is discrete. But again, if you're at long distances, you may as well treat it as continuous.
Okay.
So now, what about a fluid? Well, now we come to the interesting thing for this talk. A fluid is something like a solid. Okay, it's based on the same idea. You have rulers, but these rulers are actually a much bigger symmetry internally. The group of internal symmetry is promoted to the whole group of volume preserving diffs. Okay, in other words, all reparameterization of the phi space that preserve volume are declared to be a symmetry. If you want, this is a game, right? Constructing field theories is a demiurgic game. You invent symmetries, and then you write field theories that realize them. You may say, oh, I am against. Okay, go. You're against, go do something else. But this is the game. It's a mathematical game, and it has correspondence to the physical world often, okay? And that's why, this is why we do it, okay? I was not talking to you, Merdad. This was not an answer to you. Maybe partially it was, but it was not meant to be. But yeah, anyway, you asked also a question that I cannot answer completely. This is okay, but we can discuss that later. Let me not lose the momentum, okay? Momentum may be discrete, maybe continuous, but let me not lose it, okay? So let me go ahead on this. So that's the game. Intuitively, this is understandable when you see, when you're in the ground state, if you have this symmetry in the internal state, then this symmetry in the internal state will give you an accidental property that you visible in ordinary coordinates. In other words, if you take your fluid in the ground state and you start mixing parts of it around without compressing it, you get a configuration that has the same properties, in particular the same energy. Okay, so in other words, this symmetry is essentially at the basis of the fact. It just implements mathematically the fact that water has no shape. Okay, that's all that I'm saying here. Okay, and now you can formalize. You can write the effective Lagrangian for a state, for a system with this symmetry. What you have to do, you have to construct a Lagrangian that is invariant under this object. Okay, so understandably, this can only depend, the Lagrangian, at least at the lowest derivative order, will only depend on the volume form in this space that you can write this way. Okay, this volume, for instance, in 3 dimensions is a 3 form, so you can view it to be the star of a current, and this current is trivially conserved because it's the star of a 3 form, okay? And this current, so it's conserved, it's not a neutral current, it's conserved not depending on the equations of motion. You can view this current as the particle current, or actually more correctly in this situation is the entropy current. This is just stating the fact that the system is a system where entropy is conserved by fiat. Okay, by construction, by the way it's constructed, this system conserves entropy. In other words, there's no dissipation. Okay, because will be based on the Lagrangian. So now, using this current, you can form an invariant B, which is both Poincaré and volume preserving invariant, because the volume form is invariant under volume preserving diffs, right? It's precisely invariant under. Is the invariant object under this symmetry, okay? So this is the lowest invariant you can form, and therefore the lowest derivative action will just be a function of this invariant, okay? Which you can interpret as the square of the entropy density, okay? And now, if you now work with this action based on these fields, the dynamics is exactly the relativistic Euler equations that you find, for instance, described at length in the Weinberg book on gravitation of 1971. Okay, so in particular, let me now play a trick that I learned from Merdad. Okay, in particular, okay, here we are. Okay, the velocity of the fluid, which is related to this form, okay, here is nothing but by the way, this phi is a ruler. So I can measure x using phi, or you can measure phi using x. You can do the inverse mapping, x as a function of phi, okay? 3 fields, 3 coordinates, assuming that these fluctuations are not crazy, this is always invertible, and you go from one to the other, okay? And so the velocity of the fluid is simply the derivative of x as a function of phi, and t with phi fixed. Okay, let me say it this way. Phi, okay, and then with the velocity you can derive the Fock velocity by the usual laws of relativity, and in fact you find that the current is nothing but the square root of b times the Fock velocity, and the rho and p are just given as function of of F and its derivative. So, and then you write the energy momentum tensor, and the equations of motion are precisely the conservation energy momentum tensor, namely Euler equation. Now, there are some properties of ordinary fluid that in this construction can be interpreted in the ordinary approach of symmetries, okay, Noether theorem. In particular, as I said, this system has a huge amount of symmetry. The question is, what are the consequences of these symmetries? Well, the consequences of these symmetries are what is known as Kelvin theorem. Kelvin theorem is a known result of fluid dynamics that states the following. Here I stated in the non-relativistic limit. The relativistic limit is slightly more involved, but is the same. The essence is the same. It tells you that if you consider the flow of your system given by this yellow line, okay, this is where a point moves across time, okay, and now you draw a line in the flow, okay, closed contour, and you integrate the velocity along this closed contour, okay. You do it at one time, and then you do it a second later, when this contour has been brought forward by the flow, and you do again the same computation. What you find at this is that this integral remains the same. In other words, that the integral along closed contours is conserved along the flow. Okay, so that's one property, one standard, well-known property of fluids that you can interpret in this construction by the usual rules of Noether's theorem. Of course, you can simply derive, in the standard case where you derive without a Lagrangian approach, you just write Euler equation, and then you check that this thing is true just from the equations of motion. Here, we derive it from Noether theorem, which of course relies on the equations of motion. Now, another property of fluids that becomes manifest.
Sorry, what symmetry will lead to this if I want to do Noether procedure?
No, okay, this symmetry, there is a transformation. I don't even need, you see, there is, the Lie parameters are local in this case. They're local in space. They're local but time independent. So it's like so the conservation law, the conservation law is not the conservation of a current. It's the conservation of something local, in a sense, okay? If you want, the conserved charges are the integrals along any closed contours.
Okay.
These are the conserved charges.
Okay.
Another property, remarkable property, which follows from the symmetry and which is intrinsic, well-known property of fluids, is that when you expand, as you see, fluids have three fields, right? Have 3 degrees of freedom, like solids, okay? On the other hand, there's only one fluctuation of fluids that is very famous and that we have been using in this moment. And these are the compressional excitations, the longitudinal modes, the compressional modes. While in a solid, all the 3 phonons are famous, right? There are phonons that are compressional and transverse. They're all good to send signals. But in a fluid, only the compressional modes are traveling, giving rise to waves that travel, okay? Imagine we were giving this talk in a solid. I would be able to communicate with you on 3 channels, okay? While in a solid, so I would be able to give, maybe even by combining, I would just be able to give the talk in a third of the time, okay? Something like this. While here, I have to use just 1 channel. Okay? Of course, you would have brains that work in a different way. Maybe the brain will be 3 times slower, okay? So then that thing will change, okay? So anyway, this phenomenon is just reflected when you take the quadratic action for a fluid, okay? You expand like around the solution, you expand, and then what you find is that just as a consequence of this symmetry, namely of the fact that the Lagrangian is just a function of the of this B here, this determinant, it's a volume form, okay? Then if you decompose, if you look at the time derivative part and the gradient part of the quadratic action, you find that the gradient part only involves the compressional mode, the longitudinal mode. It's just the divergence of pi. As you know, you can write pi as the combination of the longitudinal and the transverse. The longitudinal is just a gradient. The transverse is a curl. There's no curl square here. Okay, so the curl part of the fluctuation, which is the transverse one, has only a time derivative. So it's not an harmonic oscillator. And this changes the rules of the game, or if you want, even the notion of reductionism in the following, in a very dramatic way. Okay. Now you see, for longitudinal modes, you have the ordinary linear dispersion relation, omega equals speed of sound k, which tells you that to excite, for instance, short distance mode, to really probe the UV, you need to excite the system with very, very high frequencies. Okay. If you are at very low frequencies, you will never see the short distance. On the other hand, the transverse modes formally have no frequency. Okay. So, I mean, they have no potential part. So for any momentum, naively, I mean, at least at face value, their oscillation frequency is 0. Okay, they're not oscillating. It tells you that for any k, even arbitrarily small, even arbitrarily high k, which is short distance, the associated frequency can be as low as possible, as thinkable. Okay, in other words, it means that in a fluid, even at very low frequencies, you can in principle excite short modes. And this is the essence of turbulence. Okay, turbulence, what is the phenomenon of turbulence? You start moving around your big pasta thing. Okay, you move around with the spoon, you create very big vortices slowly, and this becomes smaller and smaller and smaller and they create smaller vortices moving with the same frequency. And these smaller vortices at a certain point will become as small as the UV cutoff of your fluid description. And at that point, it will dissipate in other degrees of freedom. In other words, a fluid, the way we think of it, just because of this, unavoidably, classically, will drive something that we do macroscopically to short distance and will turn all our motions into heat. Okay, and heat means that we are heating the UV. Okay, and if you want more correctly, I mean, actually, the transverse mode, I have an equation of motion like this at the linearized level, meaning that the solution, I mean, is not an harmonic oscillator, but something that is given by a constant plus something that grows linearly in time. And what is this? Okay, well, this is just the linearized description of the motion of a vortex. Okay, if you just take angular coordinate, this is precisely if you take a vortex like a hurricane, and you just look at the fluctuation, okay, this is precisely what it is. It's something that moves linearly in time. If you want the angle, if pi were the angle, that would be the exact solution. Okay. So that's the essence of so you already see that the fluid is intrinsically, because of its symmetry, the symmetry of the fluid seems to be also its doom in the sense of effective field theory, because when you think of effective field theory, you say, I want to describe things long distances without knowledge about short distance. Well, it seems like for fluids, one way or another, you're driven to short distance because of this property here. Okay, and the leading order correction from short distance in the equation of fluid is given by the Navier-Stokes equation, which implements this dissipation. But I will not be going to discuss this. I will strictly stick to perfect fluid. I really want to think, can I now take this system and grind it through quantum mechanics and ask myself, how will it work? Does it make sense to do that? Okay, that's what I want to do. And I already gone through half an hour, which is not so bad, but still. Now, in order to study how this happens, it is convenient to zoom in on these transverse modes. And you can do that by focusing on a regime where the fluid moves very slowly. As it is intuitively clear, when things move slowly, they don't make noise. Okay. And in fact, in this regime, you can integrate out sound and derive, in other words, integrate out the transverse mode. One way to do that is to go to a compact space, to compactify space, and then work in a regime of very small frequencies. If the frequencies is so small that the wavelength of the lowest wave you can emit is longer than space, you will not emit sound, okay? So if you go to this regime, you can effectively describe your system in the following terms, okay? Let's imagine space is compact. It can be described in the following way. The degrees of freedom amount to a mapping between some external space, phi, and physical space, or the other way around. These two spaces are diffeomorphic. Let's even think they are isomorphic in a sense, okay? And this mapping is volume preserving, okay? In other words, the dynamical variable is precisely the mapping. And time evolution is the evolution of this mapping, okay? At a certain time, I do a trivial mapping, and then at future times, the mapping changes. That's my dynamical variable, okay? And the velocity, the main dynamical quantity, which is just ddt of x of phi t divided, ddt, okay, that's it, okay? And if you take the Lagrangian, I started with in the beginning, at the lowest order in the derivative expansion, it will just be given by a function of v, okay? And relativity dictates as a function of this form, but okay. But the regime where you only have the transverse mode is the regime of low velocity, which is always the regime of non-relativistic flow, which is to say that you're forced to expand this quadratically in v. So that's what you get. So this is the Lagrangian I will focus on from now on, is a quadratic Lagrangian in the velocity, where the velocity is the derivative of this mapping x of phi of t, and this is a volume preserving mapping. Now, the first thing is, can we guess quantum mechanically what the energy levels will be in a system? Or if you want, given the configuration of momentum k, what will be its energy? Okay. Let me give you an idea. This Lagrangian, if you forget for a moment the constraint of volume preserving, which can be implemented using the usual complicated Dirac procedure of Dirac bracket, which I don't want to do here. It's doable, it's a bit boring, you can do it, but let me not bring it up, okay? So it looks like a generalization of the Lagrangian of a free particle, where the role of the mass of the free particle is played by rho. Now, for the Lagrangian of a free particle, this structure translates into this for the Hamiltonian, written in terms of the momentum. In other words, the mass from the numerator goes into the denominator, okay? And then the energy levels go like this, k squared over m, okay? If you want, once you say that the mass is below, by dimensional analysis, you know that the energy has to go like k squared. Okay? Now,
Rho is constant here, right? Rho is constant, right?
Rho is constant.
Okay.
Rho is now a constant, right? Because it's incompressible.
Okay. Thanks.
Good. No, it's a good question. Okay. So now I have a fluid. Okay. Let me not go through it. I have a Lagrangian like this. Well, you're not surprised that the Hamiltonian will be 1 over rho times some complicated things that the Dirac bracket, you have momenta, all the crap. Okay. But it's 1 over rho times some dynamical variable that are just the fluid analog of the momentum. Okay. In fact, it's going to be the velocity itself. I mean, the velocity, the conjugated momentum. Now we can guess, based on this and dimensional analysis, what the energy levels will be. And we can make two broad, I mean, I'm guessing here, I'm not doing computation, I'm just doing guess, and I'm applying dimensional analysis. We can do consider two broad situations. One, where the only dimensionful quantity we'd have at our hand are infrared originated. In particular, if we have a fluctuation with momentum k, the lowest fluctuation with momentum k, then k is the only available scale. And let's say we are in 3+1 dimension, rho is dimension energy to the 4th, then the only possibility for the energy dispersion relation is this, k to the 5th. I mean, something that moves very, very slowly at low momentum, but yet it moves. Eppur si muove. Okay, moves very, very slowly, but it does move. Unlike the fluids, ordinary fluids. I mean, this is very different than what we were having here classically. Okay, this would be a quantum phenomenon. Okay, and that would also mean that we are not forced to get into issues with UV. I mean, viscosity. I mean, we're not reaching short distances because there is, I mean, at any finite momentum, there is some gap. Okay. I mean, it goes slowly with K, but it goes. Okay. So we cannot go to arbitrary distances, large K with fixed energy. Okay. This is very important. Or we could have an even more dramatic situation where the dispersion relation has UV dependence. In other words, very much like we were thinking classically that the UV will matter, it will matter big time also quantum mechanically. And meaning that the system per se cannot be defined without the definition or the addition of a UV scale. So it looks like it makes sense quantum mechanically, but no. If you want to make sense of the path integral of this object, you have to introduce a scale. And then that scale is part of the game. Let's call the scale lambda, which is essentially we interpret it as the cutoff. And then a possibility then is that the energy is like that, which is a huge, dramatically different change with respect to the classical situation. In the classical situation, you had no gap. And quantum mechanically, these guys are basically at the cutoff. Now, it turns out that this hypothesis is the hypothesis that Landau made, at least, I'm not sure he presents it as an hypothesis. He says it's like that, okay? And Landau, in such a way, he gets rid of these transverse modes. And because he had started trying to quantize a fluid, an ordinary fluid, he had these 3 degrees of freedom. But in my mind, this is what I think, he wanted to explain superfluids, where from phenomenology, it was evident there was only one mode macroscopically. And then this came very handy. He got rid of the transverse modes, and he was left with just one mode, which is precisely the one mode that you have in the superfluid. Now, my question now is whether Landau is right or wrong, and whether there is another option than just this. In fact, there may even be some intermediate option. Let's say lambda to the cube p k squared. It can be some combination. Okay? And this is what I'm going to investigate now. Maybe we can take a little break and ask questions, and then I start with the second part of the paper, of the talk. No, Marco.
Riccardo, can you remind me again? Sorry, going back. Can you remind me again?
Gabriel. Okay.
Yes,
okay.
it's yes. I am Gabriel. Yes. Can you remind me again the story about the circulation theorem? Because I mean, it's not an integral over a surface as typical charges, but it still arises as a normal symmetry.
Yeah, but because this transformation, I mean, here the Lie parameters themselves have indices. So then you can integrate on different objects. So, and they are localized. So this is what I remember doing. You at the end of the day, you can do it this way. Now, if I have to sit down and write it in paper how it works, I will get confused. I'm pretty sure.
Okay, so you say eventually it's as if the current has actually 2 indices rather than 1,
right?
And this provides you the
right.
Thanks.
Maybe Alberto remembers how to derive it.
Are you talking about the Kelvin's theorem?
Yeah, no, using the but we will do that later. Otherwise, we will.
Yeah.
Okay.
Sorry, I have another question, Riccardo. So when you do this dimensional analysis with rho at the bottom of the dispersion relation, so have you taken at some point the non-relativistic limit, or are you doing the fully relativistic case?
I'm non-relativistic here.
Okay, then there is another. So now K and energy have different units formally. No? Because in non-relativistic limit, the speed of light is...
no. Okay, in this limit, rho, okay, very good. If you want to take this limit, rho is mass over length cubed.
Yes.
And that's it. And this fixes, and k is 1 over length.
Okay, so those, you're saying those two are already dimensionally correct. Okay.
Yeah.
Okay, thank you.
Yes. And lambda here is a length.
Inverse of a length.
The inverse of a length, yeah, inverse of a length.
Thanks.
Okay. So this is non-relativistic. Okay. So now in the second part, I will show you how to answer this question. I believe I have an answer to this question, and I think this answer is the correct one. Okay. And now, in order to explain what I will be doing, let me just step back and let me just ask again. So what are we doing here? What are we doing here? So we are doing this, as I said, we are mapping a field manifold into a space manifold. Let's say that they are isomorphic. This is like a brain, okay? We embed the brain into space. It's like a 3-brain embedding space. Only that this 3-brain has a bigger symmetry. You can put it around like a Nutella thing. You can just mix it, okay? It's a Nutella brain, okay? Now, so the dynamical variables, as I said, are all the mappings. So the dynamical variables are elements of a group, the group of volume preserving diffs. Given that these manifolds are isomorphic, I can view this mapping as a mapping of a manifold into itself. So it's a group, okay? It's a volume preserving group element. So the dynamical coordinates are the elements of a group. And the trajectory in time is just a trajectory of a point on the group manifold, okay? And like all the time that there is a trajectory in a group manifold, like all the time there is a group manifold, I can think of the group action on the left and on the right, okay? And in this particular case, given X, I can act, sorry, I just took left and right into a mirror here, just for convenience. Left action, okay, is the one that acts on the coordinate phi, and that's a symmetry, okay? As a staunch Marxist, I'll take the left to be the symmetry, and the right is a joke, okay? For any right-wingers, this was a joke, okay? And the right is the action on the x coordinates, okay? And that is generally not a symmetry. In fact, in this particular case, it's not a symmetry, okay? So there is left and right action. Now, this state of things defines, following our friend Arnold, okay, remaining with the glorious Soviet Union, a generalized rigid body, okay? And the idea here is that very much we can study the rigid body in quantum mechanics with a slight motion of fantasy. We can study an incompressible fluid. Now, why a rigid body is related to this? Well, imagine a potato, okay? Take a potato and imagine what is the configuration space of a potato. The configuration space of the potato is given by all the possible O3 rotations with which you can reorient your potato, okay? So the configuration space of a rigid body is an element of SO3, okay? So, and now you can generalize this, in fact, to any group, any potato living in the joint of a group, and then you act with the group action on it, okay? 3 space is the joint of SO3, okay? In fact, let me explain this, again, using the tricks of Merdad. There is little things written there, okay? So take a rigid, so what is the situation with the rigid body? Okay, so you have, let's say that these 1, 2, 3 bar are the coordinate axes of the experimentalist, the lab frame. And the yellow axes are the frame fixed with the potato, okay? It's just 3 toothpicks just into the potato, okay? And of course I can put the toothpicks in different ways in the potato. And if I put them in different ways, I will choose different frames the tensor of inertia with respect to this axis will look different because the potato is pretty potato-like, right? It is very different, okay? So this is to tell you that here you have two frames. You have the laboratory frame, and if you change this frame, the laws of nature will look the same. That's a symmetry. And then there is the potato frame. If you rotate this frame with respect to the potato, things will look different, okay? In particular, the tensor of inertia will look different. And the configuration of your potato is given by a matrix O alpha bar alpha that intertwines these two reference frames, that brings one frame to the other, okay? And the action of the symmetry on this dynamical variable, which is the 3x3 matrix that relates the potato in the two frames, there is action on the left, which is a symmetry, the rotation, essentially here you are rotating the experimentalist, okay? And you can rotate the experimentalist as you wish. You can put the head down, it will always work, okay? While if you rotate this, things will look differently, okay? Now, the dynamical variables are the angular velocity, which are nothing but where TA are just a basis of the joint, T1, T2, T3, and this is just the Cartan form, okay? And the Lagrangian is simply a quadratic form in the angular velocity. Notice this is precisely the construction that you do for a sigma model, okay? These are precisely the things that people do in composite Higgs do every day, okay? This in the pi on Lagrangian, this is just the time, the d mu pi at lowest order, okay? These are the d mu pi symbols, okay? And now, okay, so you have this, you have naturally these two, yes?
Are these like global symmetries or this G dependent?
Oh, it's all global.
Okay.
This G is global symmetry, is time independent here.
Okay, thanks.
So here there's only time, right? So there's no space. Okay. Okay, very good. So you can think of both left and right rotations, okay? And left rotations are a symmetry, so the corresponding charges are conserved. Right rotations are not. However, as you're familiar from mechanics, what are the generators of right rotations? They're simply the generators of left rotations projected on the axis of the potato, okay? The generators, and you can check this in Landau mechanics or Landau 3, they're just related to the left rotators by the matrix itself, by the degree of freedom itself. By the way, you have to put a minus here in order for L and R to satisfy the same algebra, okay? And this minus here is simply coming from this minus here, okay? And the dynamics then, going back again to mechanics, as you know, the projection of the angular momentum on the axes that are solidaire with the potato are simply given by the angular velocity contracted with the energy inertia tensor. And then you can write your Hamiltonian as a quadratic form in the angular momenta projected in the frame of the potato, divided by the matrix of the inertia. Now, this situation is mimicked completely for the fluid we are considering, okay? And let me, for simplicity, focus on the case of a two-dimensional fluid. From now on, I will focus on 2 dimensions because this is the case I can solve. It's way simpler than 3 dimensions. And let me also focus on a 2-dimensional fluid in a torus, okay? From here on, let's think in terms of a fluid moving on the torus. Then you have a very similar situation. What do we have here? The role of this matrix omega is played by the mapping between the space phi and the space x. It's a volume preserving mapping. You can change the shape, but you keep the volume, okay? And the analog of the angular velocity is just x dot, is the x dot velocity, okay? And the analog of the inertia tensor is rho, and if you want this integral here, integrating over this, okay? That's your inertia tensor. And then the action, the left-right action is what I told you before. You can either act with volume preserving diffs on phi or on x. And this is a symmetry and this is not. This is why I call this one left. Mathematicians like Arnold call this right, okay? And they say, well, the difference between the rigid body and the fluid is that in the rigid body, the left generators are conserved, and in the fluid, the right generators are conserved. I instead define things in such a way that it's always left. Okay, that's okay. So then the system has a doubling of this operation. The volume preserving diffs is doubled, but only this one is a symmetry. And then what are the conserved charges here in 2 dimensions? The conserved charges are nothing but the vorticity, okay, the curl of the velocity, and they are equal, in fact, up to a sign, only that the conserved vorticity, the left, is the vorticity written as a function of phi, while the right vorticity is the vorticity written as a function of x. Now, turns out that this one here, being along the flow means keeping phi constant. So this one is conserved along the flow, meaning that its partial derivative with respect to t for fixed phi is conserved. So in a sense, this quantity is conserved, okay, as a function of phi. On the other hand, Rx is only conserved along the motion. So its time derivative is different than 0, but it still satisfies an equation of this type. But of course, strictly speaking, this is not conserved. Okay. And now you can go through exactly the same way as we did for the rigid body. Now you can very much like here, you can write the conserved the right-handed charge in terms of the inertia tensor times the velocity, or write the velocity as the inverse of the inertia tensor. If you want, you can write the e to the minus 1 alpha beta r alpha equal minus omega beta. Okay, so the velocity here, you can do exactly the same. The velocity of the fluid is given by the right-handed, well, there's even a row here that I forgot to put, okay? There's one of a row here, okay? And this is the full, this object here, this derivative, and there is inverse Laplacian, this epsilon, this is the analog of the inverse inertia tensor, okay? And then when you write the Hamiltonian, is nothing but the charges integrating over space divided by the inertia tensor, okay, which is just minus the Laplacian. There's also a contribution from global motions, like when the fluid moves homogeneously across, but this, when we take the volume to infinity, this does not contribute to the energy. So for the time being, we can neglect this, okay? Now this, so far, it's classical, and we can think of the Poisson brackets among these quantities, which then they are immediately transferred into commutators when you quantize, okay? And what happens here...
Can I ask a question?
Yeah.
So was it just a fancy derivation of what you wrote before, 1 over rho v squared at the end of the...
Yeah, this is just one of this is a fancy way of writing v square in terms of these charges, sure. Yeah, but the thing is that these charges are the generators of the symmetry, so these charges satisfy fixed algebra, okay? It's like saying that R satisfies the algebra of angular momentum, while omega does not, or it does modulo the inertia tensor. So for familiarity, it's better to write things in this term, right?
Okay.
Is that okay?
Yes, thanks.
So on the torus, it is convenient. So the algebra, well, of course, we know very well this algebra for the ordinary rigid body, while for the torus, it is convenient to work in momentum space and to write the algebra of the right generators, which is the same as the algebra of the left generators in momentum space. And what you do then you find that the algebra is this. It's a sort of, I don't know, W infinity algebra is the symmetry. I mean, this is the algebra of volume preserving, of area preserving diffs in 2 dimensions, okay? It's something that is known to stringers, okay? Less known to phenomenologists like me, but now I had to learn it, okay? So this is like some, call it, I don't know whether this is, call it the W infinity algebra, Marco.
I think it's called a sort of Virasoro algebra with central charge equals 0. It's Virasoro with central charge equals 0, I would say. But people more expert, competent.
Well, this is not Virasoro. This is a wedge product.
Sorry, there is a wedge product. I don't know what it is.
It's a wedge product. No, this is not.
I don't know what it is.
It is a wedge product in 2 dimensions. Okay.
Yeah.
And
Riccardo, can I ask you a question? Because
let me just finish the little trick that I learned. Again, I keep saying it from my dad. And now you can write your Hamiltonian in terms of this Rn, and here it is. Okay. Don't look at the coefficient here because R is the radius of the torus. This is what it is. Okay. And now I want to study this. Okay. And how much I have? 5 minutes.
But you can take a bit more if you need. I mean, there is no problem.
How much can you give me? 10 minutes? 15?
Yeah, 10 minutes, sure.
Okay. Marco, cosa c'è?
Yeah, Riccardo, sorry, it's a stupid question, really. I'm not sure I understood the symmetry pattern from the volume diffeomorphism. Can you summarize all the symmetry you are playing with from the volume diff, the left and right, this SO3? I'm a bit confused by the group pattern. What is local? What is global? At some point,
no, there's nothing local. We're only doing global symmetries here. We are doing, look, a fluid is just a region. Okay, let me just say the following. Here I described, okay, very good, very good. I forgot to say something. Here I described the rotating potato, right?
Okay.
Did you follow more or less what I said here?
Yes.
Okay. Now, did I make any reference to SO3? Was it crucial that this was a 3x3 matrix? No. All the construction could go through if these are the generators, say, of SUN. And these axes here are the adjoints of SUN, n squared minus 1. So, and this would be a potato moving in the adjoint space of SUN.
Yeah, if you wish, my question is, no, this is clear to me.
No, let me just say, because then I can do any group, I can do bigger groups. I can even do crazy groups, continuous groups, I mean, infinitely groups like the volume preserving diff. And this all I'm saying is that our fluid can be viewed as a rigid body in such a group with a specific choice of the inertia tensor given by this. That's it. A fluid is a rigid body in the volume preserving diff with a specific choice of inertia tensor.
Yeah, but then it doesn't. So you're saying it's a sort of integrable system with an infinite number of charges? This is what you are saying?
Maybe this is what I'm saying. You will tell me at the end. I'm not
okay.
I'm not sufficiently fancy. Sono fenomenologo, dai, Phenomenology, okay. Phenomenology. No, but this is what I want to learn from you guys. Yeah, maybe this is integrable. Alberto, do you think this is integrable? Maybe this is integrable. Yeah,
so
maybe you're right. Maybe the stuff we were discussing last night is precise integrability, but we will get back to this. Okay. Okay. Good. So now you see, all I said here applies to any group. Okay. This can be done in any group. Okay. And all I need to do to compute now quantum mechanics of the spectrum is to find the Hilbert space where to represent this Hamiltonian. This is a Hamiltonian that describes a point particle moving on the group manifold. So in order to construct the Hilbert space, I have first of all to construct a complete set of L2 functions on the group manifold. I have to find the complete basis on the group manifold, viewed as a manifold. This will give me the wave function for this particle moving on the group manifold. A particle on the group manifold is a potato moving in the space of the adjoint. Is this clear? The group manifold is a space with dimension, the group, the Lie group Lie algebra. And so, and this is equivalent to a matrix that describes the configuration of a rigid body. Is this clear? Okay, very good. Now, it turns out that the basis of function which is essential to derive the spectrum quantum mechanically on the group manifold, is given through the Peter-Weil theorem. The Peter-Weil theorem states the following. Given any Lie group G, a complete set of L2 orthonormal functions on its group manifold is given by the entries as a function of the group element G of all its representations. So take any representation R. R is the index that characterizes a representation, which for angular momentum is 1/2, 1, 3/2, and so on. And then take the corresponding representation, which will have dimension 2j+1 squared, okay? And then consider all its entries as a function of the Lie parameters, okay? Which parameterize the Lie group, okay? These guys give you a complete set of wave functions on the group manifold. So the group manifold, therefore, I mean, the Hilbert space, therefore, decomposes as a direct sum of Hilbert subspaces. Each of them has the dimensionality of the dimension here squared, the number of entries in the, I mean, it's the square matrices. So each of these blocks has dimension dr squared. So for instance, in the rigid body, it breaks down into a direct sum of subspaces, each of dimension 2j+1 squared, okay? Which is the dimensionality of the matrices representing spin j squared, I mean, the number of entries, okay? And in these wave functions, on these wave functions, there is the natural action left and right of the symmetry, because the wave functions themselves are matrices representing the group. So the action to the left is simply multiplying by the same representation to the left, and the action to the right of any element. This represents this element, okay? So I can build Peter-Weil gives me, it already solves the problem for us. It gives us the Hilbert space and how this transformation acts on the Hilbert space. In particular, you see the action of the right, which is the one we are interested here, sends each of these blocks into itself, because it sends this dr by dr matrix into itself, okay? So it means that the Hamiltonian, okay, which is just a function of the right generators, okay, decomposes as a direct sum of blocks, each of them acting on this subspace. This perhaps is the essence of what you're saying, integrability, Marco. You see what I'm saying? It really decomposes into this block form, but maybe, but we will get maybe to that later. So, and that's it. Now we have to find the spectrum. We simply have to study each of these blocks. And these blocks are finite dimensional, okay? Each of these blocks has dimension dr squared. So, which seems a big dimension, especially, but notice that, okay, well, each of these blocks has this dimension. However, in this block, both the left and the right generators act. And the left generator acts precisely like this representation. So that means that it's going to be the energy levels, given that the left and the right generators commute, the energy levels have a degeneracy, which is given precisely by the action of the left generator. So you have dr degeneracy. So in other words, you have in principle dr different levels, each of them dr time degenerate, and this makes dr squared states, okay? And just to give you an idea, for instance, for the rigid body, each block has this dimension, and this multiplicity, even though the degeneracy, so this will give you, in principle, 2j+1 eigenvalues, each 2j+1 time degenerate. And this is understood as follows, okay? You see, take your rigid body and take a state of angular momentum J, okay? Now, there are two types of operations that you can do without changing the angular momentum, okay? One is rotate the experimentalist, and that is a symmetry. This does not change the energy. And this has to do with these two j+1 degeneracies. The other is to rotate the angular velocity with respect to the potato frame, and that changes the energy. And this will give us the 2j+1 energy level. So if you rotate rigidly your system compared to the lab, then you don't change the energy. Okay, and this is why you have this double degeneracy. Now, in principle, now we know how to do that with the rigid body. We would like to do something similar for a fluid. But for a fluid, the group has infinite dimension. So instead of wave function, we will have to have wave functionals, and everything will be more complicated. However, luckily, at least in 2 dimension, there's a well-known result that goes back to the early days of, I think, string theory in the 80s, even slightly before, that states the following, that the volume preserving diff on the torus is equivalent in a certain sense, which I will specify in a moment, to SUN with n going to infinity. And this is seen, okay, now I'm really going out of time. So, sorry, how much time do I have?
I mean, how much more do you need? I don't know how much this goes on.
I don't know. Look, I can do the following. I can wrap up. If there is 2 or 3 people are interested to hear the final story, which is, I think, is interesting, then I can take 10 more minutes.
Yeah, okay, let's do that. I don't think we don't have like a cutoff on discussion.
But I'll try to be. There were also questions, okay, but that's okay. But not.
Yeah, sure.
But anyway,
can,
look, it's okay.
And then we can.
This is the way you construct this equivalence. This was invented by Toft. Okay, so take SUN, take n by n matrices. And in fact, let me label the entries as, let me take n to be odd, okay? So that I can label the one in the middle 0. This is n minus 1 over 2, and this is minus n minus 1 over 2. I think it's convenient to do it this way, okay? So the indices in the matrix go essentially from minus n over 2 to plus n over 2, including 0 in the middle, okay? So it's n of them, okay? And so let me consider these 2 matrices. H is a matrix which has all ones above the diagonal, and then there is a 1 in the lower corner here. So this is a unitary matrix. Essentially, it's a matrix that shifts back on the fundamental. It acts and it moves entries 1 by 1 unit, okay? And then we consider this other diagonal matrix, which is where I spread all the n roots of the identity in the following way, okay? This is 1, and this is the one that goes almost to minus pi, and this is the one that goes almost to pi, okay? So this is the root of the identity. These 2 matrices are both unitary, okay, and they do not commute, and their commutator is given, is given precisely by this root of the identity, which is, okay. Now, I can form now the following set of n square matrices, where n1 and n2 are integers moving in this range, okay. Now, these are n square matrices, and if you choose n equals 0, this is just the identity, okay. And all the others, the remaining n squared minus 1, are traceless, okay? So they are a basis, the real and imaginary parts are a basis of the Lie algebra, okay? So of course they are complex, but simply they are a basis of the complexified Lie algebra. But so this, if you take away the identity, these are just the basis of the algebra, okay? And the commutation relation of SUN in this basis take this form, where you start seeing this n wedge m, which is what I was seeing before in the volume preserving diff. Only that there is a sign. Now, the thing becomes equivalent to what I had before in the regime where n and m are small enough that I can expand the sign at lowest order. Particularly, this is, in fact, it is convenient to rescale these generators in the following way so that the algebra will really be the one that we had before. Now, if I now consider the rescale generators, and I go, the commutational relation has this form. If I take the regime where this n, with these numbers, n1 and n2, and m1 and n2 are less than root n, not n, root n, then I get this. I get precisely the algebra before. But notice that this is true only when n is large. Let's say n is 1,000,000. This is only true with little n and little m less than 1,000. So I'm constructing a huge thing. Say I have 1,000,000 points but only 1,000 of them are good. This is like gold mining, okay? And I claim that this small set is the one that describes the fluid. And the rest is some very clever UV completion of the fluid, okay? A UV completion that is deforming and not breaking the constituent symmetries, okay? So the basic idea is that now the SUN rigid body offers a UV completion of the perfect fluid. And at this stage, you should be convinced that I'm on the right track, okay? Because this is just a rigid body. This is now a totally well-posed mathematical question, okay? So let me explain better what we're doing here, okay? Now, this index little n, which is the momentum, okay, on the torus of our fluid, before it was taking infinite values because this torus was a continuum, okay, of space. It's compact but continuum. Here, these quantities n take still integer values, but only up to n over 2, okay? And in fact, the ones that describe the fluid even take less, take square root of n over 2, okay, less than that, okay? So that means that in this construction, intrinsically, our space is a lattice, okay? When momentum it goes only up to a finite thing, a finite value means that there is, you cannot go to arbitrary short distances. The shorter distance you can go is the inverse of the momentum, and that is finite, okay? So now, with this interpretation, now we can interpret so this is Rn.
Ricardo, sorry, it's a stupid question, but I have to ask you now and not after, otherwise I don't understand. So can you go back to the, when you take this here? Yeah, so it seems to me that if you rescale R, which you can always do that, you can take the other limit where the ratio remains constant, no? And then, so I just wanted to understand.
So what do you mean the ratio remains? So
the Lagrangian
limit. No, if I rescale R, I only rescale this object here, but its dependence on n and m. See, what matters here up to rescaling is how this object here depends on little m and little m.
Yes,
if
no,
it's a sine, it's one thing. If it is linear, it's another.
I'm saying the following. I would like to understand that the normalization of the R that you have chosen, which has an n power in front of j, because otherwise it looks to me that you can take other limits. For instance, the limit in which the ratio of little n over capital N is fixed.
If I really want to define this question is the following. I could have never have written j. I could have started right away with R with the n in front, and then you would not have asked this question. The reason why I put j is because j is unitary. So it's good because it's unitary, and it will be useful later. R is the guidance that is, I mean, you can normalize your algebra as you wish, right? So what is the question? Don't understand, Marco, excuse me.
No, the question is very simple. It's only with this normalization that in the large n limit, the sign and the n cancels. That's why it's a simple question. Then you get...
No, sorry. No, cazzo.
No?
Seno di alfa.
Yeah. What do you mean? Yes.
Okay, so in order for alpha to be much less than 1, this product here, n times little m, should be less than n. So I need n times
Riccardo, this is
m.
clear, but this is precisely with this normalization of R. Otherwise,
but this has nothing to do with the normalization. N and m are not, they are integers. They cannot be normalized. These n and m, little m and little m, are momenta, if you want. They're 1, 2, 3. I cannot rescale them.
Sorry, maybe it's so simple.
Yeah.
The capital N in front will change if you rescale the generators R in another way, because on the left you have 2 R's and on the right you have 1 R. Then if I change the definition of R, the power of N there can be...
Exactly, I chose it. I did this rescaling in such a way that when I take the limit where I expand the sign, I don't get a 1 over n here, but I get a 1.
Precisely.
And it's already normalized the way it was normalized before.
Exactly. So I was, since there is another limit you can imagine, the limit in which little n over capital N remains fixed. So in the limit, you look at the large charges, so to say, that would make sense if you scale in another way.
Little n, no. So what is the other limit you're talking about?
Little n over capital N fixed. So you send both together to infinity, but the direction remains fixed. In this case, with an appropriate power of R, you will get a finite.
I keep not
result.
understanding. The only way I can expand this has nothing to do with the normalization of R. This has to do with the functional dependence of the sign.
Yeah, you will keep the whole sign in this case. That's
I don't want to keep the sign. You see, let me put it this way.
Yeah,
this is the commutation relation in the continuum. You see, this commutation relation, in a sense, has a power here that grows like a quadratic power of the momentum. This is related to uncontrollable UV behavior. Here, I regulate this. In the SUN, this is regulated into a sign. So this power behavior is regulated by the sign. But in the tail, at small little n and little m, it's exactly the same behavior. So essentially, it's like when you have the Higgs, there's a quadratic divergence, and then I regulate it. But I say that the standard model is the theory below which is in the regime where still you have this quadratic dependence. Is it clear what I'm saying?
No, I think it's okay. Yeah, sorry, go on, because it's
okay. So now you see, now I have a lattice. I have a lattice space. Okay. So here I have my coordinates on the torus. This is the torus length, and now it means that I basically have latticized the torus, each direction of the torus, into n points. Okay, and there is this fundamental lattice length, A0, like lattice people, it's the length of the torus divided by n. Okay. However, and momenta are simply given as usual by Ni over R. Okay. And now, however, based on what I told you before, these momenta go from 1 over R to 1 over A0. Okay. From the very long momenta to the very tiny ones. However, the regime where the system can even imaginarily behave like a fluid is the one where these Ni here are less than square root of n, not n. In other words, the momenta have to be less than this quantity here, and this corresponds to a scale, the inverse momentum, that is intermediate between this volume and the fundamental lattice length. Okay, it is a length that in the units of the fundamental length is here, it is square root of n. Okay, so this is what I call A1. Okay, and now I can now consider 2 square root of n and so forth. So there are two ways to lattice. That in a sense, there are two lattices. There is a fine lattice and there is a coarse lattice. The fine lattice takes value 1, 2, 3, and the coarse lattice takes value square root of n, 2 square root of n, and so on and so forth. And I can draw the following picture. Okay, our torus can be written as a coarse lattice. The yellow one is a coarse lattice, and there are square root of n times square root of n points. That is to say, n points, and each square is itself containing square root of n times square root of n fine points. Is this clear? And the coarse lattice, the coarseness of the lattice, this length here, is the fluid cutoff. And what happens inside here is beyond fluid dynamics. Okay? And now I claim that I can reproduce fluid dynamics if in this setup I take a Hamiltonian. Now, choosing the Hamiltonian amounts to choosing the inertial tensor. What do I do? What is the most obvious thing to do? Is to choose a Hamiltonian where you truncate the sum up to momenta, which are precisely of the order of the fluid cutoff that I told you before. I cannot expect this to behave like a fluid if I also add contribution from the regime where the algebra is not the one of volume preserving diffs. So I cut off the summation over up to momenta of the order of the inverse coarse lattice. And then and then I can write it this way. And now you see the Hamiltonian in this way of writing things. Now this scale here, this core scale here, I interpret it as lambda, the cutoff that Landau introduced in 1941, 80 years ago. Okay, this is an 80-year-old scale. Okay, and now the Hamiltonian, if you write it properly, apart from numerical expressions that are unitary matrices and numbers, is just given by the Landau guess in 2 dimensions. Okay, in 5 dimensions you have 5, in 3 dimensions you have 4 dimensions you have lambda to the 5th, but in 2 plus 1 you have lambda 4. I should say that the question is, what about translation? Well, it turns out that translations are played by precisely the two constructive matrices H and G, and they do not commute precisely. So the system, this lattice is not commutative. This is not the commutative coordinates, the one on this lattice. However, if you take square root of n translation, if you do translation on the coarse lattice, then you get an element of the center, and that commutes. So you see, the coarse lattice where it's also you have the fluid is also the one where ordinary coordinates emerges, while at shorter distances coordinates do not behave commutatively. In a sense, this is very similar to Landau levels, as you'll see in a moment. So now the spectrum. Now computing the spectrum now just amounts to considering representations of SUN and feeding them into this Hamiltonian and compute. Now this is something you can put on a computer, okay? And that's it. So the trivial irrep, which is the singlet, well, gives you 0 energy, no surprise. The rigid body at 0, at 0 momentum is 0 energy, ground state. Then you take the fundamental. Well, let me just make a long story short. How many states are there in the fundamental? N. These states will have to do with some local fluctuations. You have n states, and you have to fill this space with these local fluctuations. What will they be? Well, the guess that you can take in hindsight, and here I go through a whole song and dance and I will not explain it, is that these n states corresponds to something going on in each side of the coarse lattice. Because remember, the coarse lattice has n sides, because it has square root of n by square root of n. Okay, and in fact, you can really take linear combinations. Okay, you can do a little Fourier transform, you play around it, and you find that each of the states of this fundamental corresponds to a vortex localized on one cell of the coarse lattice. Okay, and depending on where you put this vortex, on which of the n coarse cells, you cover the fundamental. Very good. And in fact, you can compute what the expectation value of vorticity is, and you find precisely that in the continuum limit, it's precisely a vorticity of the right unit localized over a given coarse cell. And this minus 1 over v is because we are in a compact space, and charge, which is in compact space, has to integrate to 0. So you always have this background opposite charge. This is like, the delta function. Remember, our Hamiltonian here was the sum over n different than 0. Okay, so it's the inverse. Even as here, I should say this is the Laplacian prime. Is the one that you also find in Polchinski when you do the Laplacian on the torus. Okay, so and the corresponding Green's function, corresponding charge density is given by this. So you see, this is the charge. This is the vorticity. So this is a vortex localized there. What is the energy of this guy? The energy, they're all having the same energy, and independent of the momentum, even if you take linear combination of them, they all have the same energy. These are objects that do not move. Energy independent of P. You put them there, they're there, they're vortices, okay? And notice that their energy is precisely what Landau says, up to a log. What is the log? Well, this is a vortex. You know that the energy of a vortex has a logarithmic divergence, which goes like the fundamental scale times the volume. Here it is. Okay. So Landau was correct, but he was missing a log. Of course, he didn't care about this. Now, it's easy now to construct other representations. So for instance, you can immediately, oh, by the way, this is the expectation value, but this is a very, very, very quantum state. In other words, if I take the expectation value of the square of the vorticity, it's not the square of this. So it's not, the quantum fluctuations over this result are huge, okay? So this is not a semi-classical vortex. This is a genuine quantum vortex, okay? Now, if I take now the adjoint, the fundamental, and I take, how would I construct, for instance, the anti-fundamental? Well, expectedly, the anti-fundamental will be an anti-vortex. And how do you see that? Well, what is an anti-fundamental? It is n fundamentals, n minus 1 fundamentals, anti-symmetrized. So that means that all these fundamentals have to be in a different state, all of them. So that means that there will have to be n minus 1 vortices over n minus 1 lattice size, and there's one that is left alone. And now, if you look at what the vorticity here is precisely the opposite. That's an anti-vortex. So that's the anti-fundamental, and it has exactly the same energy. And now we are ready to go to other representation. You can go to this, and so on. And now the problem starts becoming numerically more complicated, okay? These are complicated. And for all that my collaborators were able to do, I didn't do it, okay? So it all, in fact, all of the stuff here, I mean, the vast majority of what I'm talking about is to the merit of my two collaborators, Aurélien Dercy and Andrei Khmelnytsky, by the way, I should say. They've checked that these are all gapped, and they all behave roughly like multi-vortex states. The interesting, and they're all gapped. The first instance where something very non-trivial happens is when you get to the adjoint. And the adjoint is the lowest representation on which the center acts trivially, on which all translation act in a trivial way. In some way, I think this is related to the fact that it's the first representation that is not gapped, okay? And here is where Landau is completely wrong, at least in this construction, okay? And how you can see that, where an adjoint is a tensor product of a fundamental and anti-fundamental. So you have n square states. Now, these n square states can be characterized roughly by placing a vortex and anti-vortex in the n different coarse points, coarse lattice points. And now, what will be the fundamental? Well, I mean, the singlet, you have n squared. It's like the product of fundamental and fundamental is singlet plus adjoint. If I now take vortex and anti-vortex as exactly the same point, and I trace over all points, namely, I take a state which is a totally entangled over whole space of fundamental and anti-fundamental, that's a trace of all, that's just the identity. However, if I, instead of tracing completely, I take combinations that are less trivial, I get something that in first order looks like it has zero energy because vortex and anti-vortex cancels their fluctuation. But this is true only in an average sense. Quantum mechanically, this is not completely true. And therefore, there is some leftover energy. And this leftover energy is ungapped, okay? As I will show in a moment. While these ones are all gapped. So the vast majority of the states in the adjoint are gapped. So in other words, an adjoint has roughly n square states. Of these n square states, only n of them are light. But when n goes to infinity, there's a lot of them, okay? And the way the dispersion relation behaves is this. These states here, these states where the vortex and the vortex almost overlap, basically overlap, has a quadratic dispersion relation. And it behaves like a particle, non-relativistic particle with a mass given by the amount of mass that exists in the fundamental cell, okay, in the cutoff scale of the cutoff scale. While the other ones behave like this guy where the vortices are separated, they're just like vortex anti-vortex, and they are almost the classical energy of a two vortex separated by a log. So what are these objects here? We call them vortules, okay? And these are ungapped quanta. And the fact that these guys, they're ungapped, I mean, they have an energy that goes like p squared, but it's not omega equals 0 like we had in the classical fluid. So here there is a gap, okay? Which means that these guys can stand on their feet. In other words, in order to go to bigger momenta, you have to go to bigger energy. So in a sense, you have some reductionism. You see what I'm saying? You cannot go to arbitrary short distances with arbitrary small energy. This is what tells me that here there will not be the dissipation that you have in a classical fluid. Okay, this is the way it is. And now what these vortons are, they are quanta carrying a dipole of vorticity. Essentially, you can compute, you can take one of these vortons and you form some wave function for them, and you can check that the vorticity in the state has a dipole that goes like the momentum. In other words, they move in this direction, momentum p, and they have a dipole of vorticity orthogonally to them. In other words, there is that is like two vortex and a vortex nearby that go like this, and it moves in the middle. Okay, and now you can consider scattering. And scattering is done by studying what happens in the tensor product of two adjoints, because each is a vorton. And now in this tensor product, you have both symmetric and antisymmetric products. So you see, we are not having a Fock space here. So I have both symmetric and antisymmetric product of these two particles. And therefore, I can, when I do scattering, I can have a situation where they behave either like boson or like fermions. Okay. And it turns out that this scattering has a nice description in terms of an effective Lagrangian, which I write here. Okay. And it takes this form. Okay, it takes this form here. Let me eliminate this using the usual trick. I don't want to. That's it. So for boson, you have this. In the boson regime, you have this. And in the fermion subspace, you have that. And this is where P and Q are the momenta. You see here. In particular, for the boson case, the scattering amplitude is S wave, purely S wave. That's the prediction. And when the two incoming quanta come at 90 degrees, in that regime, this is orthogonal to that, meaning that P squared is equal to Q squared, the amplitude is 0. So these are particles, these bosons, that in New York, they don't care about traffic lights. Okay, so they really don't give a damn about traffic lights, avenues, streets, they go through. Okay, while fermions, actually, they bump when they go through traffic lights. Okay. So bosons are and that's a genuine prediction of the whole construction. So now my question is, has any experimentalist seen anything like this? I don't know, but this can happen, okay? That's it, that's the summary. Sorry for having taken so much time. Sorry, that's the summary. This is what I'm thinking. To me, this is the main question. Yeah, you can consider this. This is probably too complicated.
We could probably ask a couple more questions, no? If you don't have to go, since...
Sorry, guys, for being so rude.
Sorry, Riccardo.
Yes.
So I had a question about this truncation that you do. It's just, I mean, since you have this kind of 1 over n squared in the Hamiltonian, no? Small n for the modes.
You mean the Laplacian, the inverse Laplacian?
Yeah, the Laplacian, exactly. So, are you sure that when you put UV guys, they're gonna have small energy? Sorry, high energy. Like when you go to small n, which is very big since it's below.
You're saying it looks like I'm not giving any energy to the big guys. Yeah, this is in this situation, small, long, and short is you see. Honestly, when you go and look at this quantum here, let me put it this way: the energy grows when you spread them. So they behave more or less. There is this. They behave like Landau levels. that the bigger the momentum, the bigger the energy, the more the broader the orbit. In a sense, like string theory, you go to high energy, but you go to long distances. In a sense, you have this. So it's not beyond that distance is no longer the usual idea that you go to short distance and you go to high energy.
Yeah, so even if you have big representation, you can have a kind of smallish energy when there are.
Oh, well, you can have big representations that are products of adjoints.
Yeah.
Those can be light. This is we don't have a proof. We don't have a proof yet, but I believe that all the products of adjoint, I think all the products of adjoint have these soft modes, and that all the others don't. But we don't have a mathematical proof.
I see, now it's very interesting.
We only have a proof to some extent, and then by numerics, but we don't have a proof. I have to say that. Sorry, I didn't have time to say that. But this is something that can be tested. I mean, mathematically, I think there are lots of technical questions here, and which are interesting mathematically and perhaps in a sense physically, if you want. But to me, this is the biggest question at this point. I really want this question. I really want to get to this. And because if this exists, this is absolutely amazing. In my opinion, okay. First of all, Landau was wrong. That's already something. That's already, okay. Is the little revenge of the like Borghese piccolo piccolo. It's like it's like revenge.
So okay, I think Marco has a question too. I see he has raised his hand.
I have a couple of questions. One very quick. Can you remind us where crucially you used the 2D, where 2D enters into the game, and where otherwise you can't proceed?
Here. I don't know. I gave a talk yesterday in Amsterdam, and some of the stringers there told me that there may be ways of extending this beyond T2 on T3, but this is not going to be SUN. It's going to be, God knows. You see, volume preserving diff on a torus, you can treat the torus, you can cut it into matrices, like you treat the torus like a matrix, and then it's like doing SUN. I don't know, maybe it can be done. No, sorry. Maybe it can be done also on a 3 torus. Yeah, why not? Maybe, yeah. I'm aware of this, okay? I don't know whether there's a way to do this on the... Of course, even the vorticity charges are more complicated in higher dimensions. Even there, I think Gabriel and Alberto know this much better than I do. I haven't thought enough about vorticity in higher dimensions, honestly, in probably 15 years. Yeah. I don't have, but yeah, but this is the basic result. This is a result that exists. In particular, the paper that is crucial for me is this one. Okay, very nice. I think the first instance is in this thesis of Jens Hoppe. Yeah. By the way, I learned this. It is one of the few things where it was very useful to move around the corridor of CERN. I learned this from Savidi. From George Savidi.
So since Gabriel and Alberto wants to ask question, I just, okay, let's go for that.
Gabriel, you want to go or I can go?
Go ahead.
So regarding these ungapped adjoint representations, so they have an energy that goes like P square. Now, can you think of any relationship with Goldstone states? And I'm asking this because depending on how the energy scales with momentum for a Goldstone, linear versus quadratic, the counting rules are different for non-relativistic systems. So I was wondering whether you can see any correspondence with...
Very good question. And maybe this is related to precisely to this issue about translation invariance being realized non-projectively. I mean, non-commutatively here. Okay. Maybe these are the only representation where you can make use of Goldstone theorem in one way or another. But I haven't thought about this. This is a good question. I don't know. But this is good, right? Yeah. Maybe if translations are not realized, then how you can derive Goldstone theorem in this sense?
Well, you can, you're saying if translations are not realized, well, you can still say something about gaplessness versus gapped, and you can still, in your case, you still associate a momentum to that.
No, but for the joint, the joint is representing SUN over ZN. The center is realized trivially. So those translation operators, these ones here, even these ones here, commute. Because omega now for the joint gets multiplied. See, this is the translation on the fundamental. In the adjoint, here this multiplies by n. So in the adjoint, so in other words, the anti-commutational translation is an element of the center, but on the adjoint, the center acts trivially. So this may be the property that allows you to apply Goldstone theorem in this case. That would be actually very cool, but I don't know. I haven't thought about it. Yeah, let's think about it.
Yes.
No, I know that you don't care about these things because this is not the fluids that you find in the bathtub or or the tokamak. Yeah, I know.
I know. I care very much. That's why I'm attending your talk. Anyway, Gabriel, your turn.
Yes. So something very naive, but if you can explain me. So, I mean, you associated intuitively each representation to a certain number of vortices, a vortex with zero charge but non-zero dipole, and so forth, so on.
Yeah, these are cartoonish description of, I mean, more computational aspect that you could have written formulae. Yes. By the way, formula derived by Andrei mostly, and which I essentially vulgarized in this talk. But yeah, go ahead.
Yeah, but I was asking this. I mean, since vorticity is conserved, there is no sense in which this cartoon can be made more precise. I mean, we know how to treat quantum vortices moving in some medium. It might be complicated, and we know that the number of the vorticity is 1-to-1 with the number of vortices. And
no,
I think it's also
no. Sorry, Gabriel. Let me make it clear. These vortices, if they are alone, they do not move. They only move if there is another vortex.
Okay.
This is very much related to, I believe, the papers of Alberto about vortex lines, right? Yeah. I think a vortex can only move if the whole fluid moves, right?
Yeah.
Eh?
Yeah, because since boosts are broken, there's no guarantee that if you have a static solution, you also have a moving solution. Meaning,
no, but while this is different in a superfluid, I believe. In the superfluid, the vortex can move inside the superfluid.
No.
No?
No. Let's say
a ring would move, not a line.
It's the same thing. It's the same thing also for a superfluid. So are you telling me that in a superfluid
it wouldn't move a single vortex, right?
It wouldn't move as well, right? But sorry, in our paper, or there also, it moves when there is another vortex, right?
Yeah.
Gabriel.
Yeah.
Okay, it's the same thing.
Yeah, because the velocity field is completely determined by the vorticity field through some Biot-Savart integral. So depending on the geometry,
so the fact that vortices have an energy that doesn't depend on P is just this.
Yeah. That's why, I mean, since the formulas are so similar, and since you were asking about 3D, do you have any clue if this correspondence can be made some more precise?
In 3D?
I mean, if it's true, like the teach representations associated with a certain number of vortices, certain charges, then in 3D, there is the same physical picture could hold. That's why I'm asking.
In 3D, you don't have vortex lines. So
yes.
So group theoretically, how do I associate that to?
Okay, and then I have.
No, Gabriel, I mean, how to do this in 3 dimensions? What is the analog of, look, you're asking this question, okay? If I understand correctly. What is the analog of this relation in 3 dimensions? Once I know the analog of this relation, I think I can start guessing what all this thing about vortices generalizes, even before doing a computation. But until I know how to extend this, I'm not sure. Maybe, can I do VDIF in 3 is, maybe I can interpret this as SUN, as SU square root of n times square root of n. And now I do SU square root of n cube, cube. And now I can reorganize, I don't know, no, I don't think it works. Because you see, this structure is intrinsically 2-dimensional. This construction here is very much 2-dimensional. But maybe I can, maybe, who knows? Yeah.
Perhaps since it's not a question, just let me say it's a comment.
Maybe rather than matrices, I have to use 3 index tensors. Can I do an analog of this? No, but then again, I don't know. Yeah, I don't know.
Okay, so just a comment so they also can ask their question. You asked about realization in physical systems. I read recently another site that I think there is some phase of helium at 0 temperature. Normally it forms some vortex lattice stuff. If you put in some trap and you make it spin. But then if you shake it, apparently there exists some fluid state. I think something that this Pasha Wickman told me some time ago. You might, Pasha Wigman, he's a condensed matter guy who visited here some time ago. You might want to look at that. I'll send you the reference.
Very good. Tell me, I'd be curious. I'd be curious. Yeah, I don't know. Yeah, as I said, I told you honestly what I understood, and there are lots of things that I haven't yet understood. And I don't want to give the impression I understood more than I have understood.
I have a question.
Yeah.
So can you, well, this is perhaps related to the previous questions, but I think I'm more naive, so I wanted more simple answer. Can you explain the momentum in this language? Because like when we say the same particle with different momenta, as Alberto says, since we don't have boost, it's not
momentum here is, to talk about momentum, you don't need to have boosts, right? It's enough to have translation invariance.
Right, but I cannot talk about the same particle having different momenta. In general, I won't be able to identify the states with different momenta as the same.
In this particular case, in this particular case, momentum is a specific element of SUN here. And then what the momentum is the action of these specific elements of SUN.
So you fix the representation, and then within that representation, various momenta.
I have this way of writing SUN. Okay, look, I have this construction. This is Toft construction. Okay, Toft invented this piece of crap. Okay, how he did it, no idea. Okay, where he pulled this out from, no idea. He invented this. Okay, and in this construction, you have this algebra, and you have this. You have that these R's are characterized by 2 integers, and there are these 2 elements that act on R in the following way, where this is a root of the identity, which is clearly this omega this is e to the 2 pi n and I. This really looks like a state of fixed momentum, right? With momentum ni. No?
Yes.
That's it. That's all I'm saying. And starting on this, I interpret these T's as generators of translation. Notice, for instance, that when you take the fundamental, just to give you an idea, take the fundamental is alpha going from -n½ to +n½ over 2. Now, what you discover is that the states of the fundamental, when you act on translation in the 2 direction, they are eigenstates, which means that these are states with fixed momentum in the T2 direction. But when you act in the T1 direction, you go to the next, which means that the alphas are eigenstates of position in one direction and momentum in the other, very much like in the case of Landau levels. Okay. So, okay. And now this fundamental on the fine lattice, see, on the fine lattice, there are n square points. Each state, as alpha varies from -1/2 over 2 here to +1/2 over 2, fill a strip of width 1. So there are n stripped of width 1 and length n that makes n square points. But now I can take linear combination of this. I can do a Fourier transform and create a linear combination of these strips with specific coefficients, which I don't indicate here, and then you get a localized Landau level. This is precisely like in the look, in the case of Landau levels, a particles of momentum p cannot be localized in a region smaller than the classical orbit of a state of momentum p, right?
Yeah.
And this is what it is here. This is what this is.
Okay.
To Landau levels. Okay. Yeah. So I don't know whether this is addressing any of your questions, but this is just to tell you that there is a natural interpretation. I mean, the space-time interpretation I don't start here with the space-time interpretation. It emerges. In a sense, you can say that in this construction, space-time is emergent. And also, I think it plays a role that I use this Hamiltonian, because if I'd use an Hamiltonian with a completely crazy function of n here, this would have been, there would be no way to interpret this as a local object. Notice that even if here I have 1 over n square, this corresponds to v square. But if I put, for instance, 1 over n to the 4th, there would be no way to interpret this in terms of a local Lagrangian. So locality plays a role in the choice of the Hamiltonian. So I have space, and locality emerges when I choose the Hamiltonian. If you want, this is a Coulombic interaction, right? This is the Coulomb potential.
Sorry, but in the case 1 over n to the 4th, couldn't it be a local Lagrangian with the equation of motion is Laplacian square of something equals something else?
Oh, you're right. You're right. Maybe it should do the other way around then. Yes.
Or some, I don't know. For instance, some odd powers of n, probably you might have problems. And cube.
Yes, you're right. You're right. Something else. You're completely right, Albert. Yeah. Look, yeah, it's clear that you can write something crappy and be non-local. Yeah, maybe the first guess for non-locality was not correct. Although I think it is. Although I think it is, because essentially here we are regulating by putting here is like writing without this constraint. And I put here a 1 plus n over square root of lambda square. So yeah, you're right. It's 1 over box square. You're right. This is like Pauli Villars. Bravo Alberto, sì, ho detto una cazzata. So then you have to do something else. You have to put square roots or stuff like that. Yes. Hai ragione. Ho detto una puttanata.
Marco, did you have another question at some point? Seems...
No, it was a journalistic question. So at the level of really, I don't know if journalistic question was simply that it looked like that this infinite sort of global symmetry would be well, first peculiar to the 2D case, and second, yeah, it's not clear to me because certainly this system doesn't look like integrable at all. Of course.
Well, remember that in this construction, I have avoided talking about the phi coordinates. Remember, in the case of the rigid body, each level, each block has this double degeneracy. And the other degeneracy is coming from the action of these left generators that I didn't even use. So there is an underlying degeneracy on the hyperspace which doubles everything. We actually double, which I mean the joint, the multiplicity of the joint is not n squared, but n squared squared. And this I haven't used, okay? And I just work on the, if you want, the viewpoint that I don't consider any quantity that transforms under the left generators to be observable. Essentially, I gauge it. However, I can write Casimirs. Okay, I can write Casimirs. What are the Casimirs? So the Casimirs are the Casimirs of SUN Casimir. They are sum over n, jn1, jnk, delta sum over n equals 0, okay? If I take this product, these are all the Casimirs. For SUN, like I have j squared, right? These are the Casimirs. They correspond to R, okay? And they correspond, and they in each representation, in each of these representations of my system, they will have a given number or value. Now, however, these Casimirs are equal, and now these are conserved, right? These are conserved quantity, and they're equal to the corresponding left. Because remember, the left and the right generators, they are related by rotation in the rigid body. So even if I don't consider these observables, the conservation of their Casimirs, the fact that corresponds to the fact that these are conserved, even though the R's are not conserved, some contraction of them are conserved. So in other words, you see, so far I haven't talked about this symmetry. Let me not talk about it. The R's is not a symmetry because you see different states in the joint have different energy. However, the Hamiltonian is in terms of blocks that act on each representation. So the label of that representation characterized by the Casimirs is a constant of motion. What is this? How do you call this? This is not a symmetry. What the hell is it? Marco. By the way, in the fluid, this guy here corresponds to the integrals over the volume of powers of the vorticity. These integrals are all constants of motion.
If integrable wouldn't be the usual integrability we have in mind, which will have no dissipation, there will be no, there will be
there's no dissipation. Of course, there's no dissipation.
It's no dissipation and other properties, right? I mean, there should be, I mean, principle in the usual integrability, your amplitude
the usual integrability,
satisfy some
I don't know very much about integrability, so I don't know what is the usual thing about integrability. But dissipation, I don't know. What do you mean there's no dissipation?
I meant the fact that you have no way of, say, particle production. You can't produce anything, so you can't have...
Oh, here you don't produce particles as well. If you are in the exactly, that's precisely the particle number of parts. I mean, if you are in a certain representation that is the product of three adjoints, you will remain there. You will not scatter. I don't know, actually. It's a good question, but I think not. I think not. No, I think not.
No, it's not a good question.
Depends how you interpret particles, because there is a subtle fact here, is that the product of two Whartons, these are not the Fock space. See, when you take the product, there are representations new, but there are also some Whartons back to themselves, because you take the tensor product to a joint, you also get an adjoint again. So there are some subtle things that in the Lagrangian limit, these all disappear. This is why I believe that in the Lagrangian limit, 3 go to 3, 4 go to 4. I think this is still true. I believe this is true, but this is a very good question, Marco.
Yeah, as you know, however, integrability is expected only in 2D, right? I mean, we don't know, or at least modulo n equal to 4 super Young-Mills. I mean, you don't expect.
Well, this is an example of an integral system in 2+1.
But these are not space-time symmetries, right? Well, not the usual sense, right?
Well, yeah. Well,
So you have area preserved, volume preserving this in 3D, then we don't know to quantize it, but you do have the same symmetry.
Yeah, I don't know, guys.
Sorry, for integrability to hold, wouldn't you need?
Ooh, Simeon! Thank you for coming. What are you doing here?
Show your face.
Oh, no. I have to answer your message. I mean,
no.
Yeah.
Okay. Wouldn't
go ahead.
Wouldn't you need scattering to be trivial in the adjoint sector?
Yeah.
For integrability to hold.
Simeon, honestly, I don't know anything about integrability.
I don't either, but I think you need trivial scattering, right?
Really, but then it should really be a piece of shit integrability. No, but this is in one dimension.
No, wait. No, I mean,
it should be in 1+1, but here it's in 2+1. I mean, but the integrability is really not interesting.
No, I mean, I think it's too much. No,
you don't even have scattering. Come on. Then I call it. I mean, that's truly onanistic, right? Integrability at that stage.
No.
But I mean, whenever you have particles with non-trivial scattering, you can easily set up chaos. I mean,
oh, you're saying
Boltzmann's H theorem.
Okay, I understand.
Also, I mean,
there is a famous constraint that you can check in principle, Riccardo, for usual integrability, which are the Renaud-Young-Bax equation, which means that the product of 3 S matrix elements taken in an order should be equal to the matrix of 3 S matrices in another order for any possible entries, which is an enormous constraint, typically, which essentially tells you in one shot whether your model is integrable or not. Yeah, essentially on this kind. Typically so constraining that
I wish you guys you tell me what is the quickest compendium of all these things they can read to get an ability to at least address partially any of the questions you asked. So what should I study? Cosa?
No, I mean, I'm not an expert either, so you shouldn't ask me.
Simeon, where should I look at these things?
Me, I'm not an integrability expert, but
knowing some.
Ask Pedro.
Pedro, okay, we'll ask Pedro.
But sorry, to come back for a second to Riccardo's comment that if there's no scattering, everything is trivial, but you can still have phase shifts, no? Meaning the S matrix is still non-trivial.
In 2 dimensions, yeah, in 1+1, yes.
Yeah. Yes. Of course. Otherwise, yeah.
But so you're saying you can have, even in 2+1 dimension, trivial scattering with phase shifts that depend on the.
No, I think no, because of analyticity. I think in 2+1 you can't. In 2+1
exactly, because this is like Coleman Mandula, right?
Yeah.
this is the basic fact that when you play billiards, and you know that when you play billiards, you take two balls, and you know by experience that if you hit head on, they go straight, and then you sliver, and then they go by an angle. So they have all the angles. You already know by playing billiard what is the maximal symmetry of space-time you can have.
Yeah.
So every billiard player can put a bound on the symmetries of the billiard. Otherwise, they wouldn't be able to play. Yeah.
Sorry, Riccardo, I had another question, but I forgot to ask. At some point, you talk about bosons and fermions. So what is spin in this SUN way of seeing space-time? I guess it's some SO2 inside.
Sorry, so no. When I say bosons and fermions, here I didn't talk about spin. I talk about the fact that in this subspace, the time evolution of two blobs into two other blobs can be written in terms of two diagrams, which are one interpreted as T, T, and the other as U, and they are summed with plus sign. While in this other subspace, you have the same two diagrams, summed with a minus, precisely as if you were dealing with the scattering of fermions. That's all I'm saying. But by the way, nobody prevents me here from taking a state which is a linear combination of these, where the scattering amplitude would be a combination of these two. I don't see anything that super selects or stuff like that here. I don't. Maybe, yeah, I don't. Maybe I'm being dumb, but I don't. Maybe you're saying, maybe I haven't considered rotations here.
I mean, inside the area preserving diffeomorphism.
There's going to be rotations. Good question, Christian. Non ci ho pensato. Nothing. Good, very, very good questions. I haven't thought about it.
It's fine. I just wanted to understand those words.
But you see, but from the point of view, by the way, from the point of view of a rigid body, we as rigid bodies, because we're all sort of, well, I'm pretty rigid after I got this sciatic fever. I'm totally rigid, okay? Now, we are not eigenstates of the Casimir of rotations, because if we were so, we would be deoriented in all directions. So we are normally linear combination of different representation. Look, an hydrogen, a water molecule has a dipole, but it has a dipole. A fundamental particle with a dipole would break CP. But why does a water molecule have a dipole? Because a water molecule is normally a superposition of states with different total J. So all the macroscopic objects are superposition of that. So now, of course, you may say, well, superposition of bosons and fermions is complicated. Yeah, it's true. If maybe for some reason there is some way to distinguish these two, but I don't think so, because what distinguishes bosons and fermions here is the center. And these are all trivially acted upon in the center. Right? In the potato, what distinguishes a boson state from a fermion is the center action. Whether you have SU2 over Z2, so I'm not sure.
I think you can put one vortex and another around and make it.
Maybe I can do. Yeah, you're right. I can try and do something. This is something. Very good question.
Because
I don't.
You have the translation.
Buona domanda.
So,
no, I haven't thought about it. Very good question.
Okay. Do we have any more questions? Seems everybody's fine. Well, we had like quite a long discussion too, so it was very nice.
Thank you very much for being patient, and in spite of the fact that I violated all the rules of seminar giving as usual.
It was very interesting. So also we don't have a lot of constraints in the virtual stuff. I mean, people can just leave the meeting, you know. So
at 5 we have another. Riccardo, at 5 Passera is going to talk about G-2.
Non perderti la Passera. Ascolta, Marco, l'abbiamo già visto Passera. We saw a seminar he gave last week at the Institute. Absolutely beautiful.
Oh, excellent. Thanks.
Both the speaker and the audience were at the top. So that was very good.
Okay, good to know. Thanks a lot, Riccardo. Really interesting. Looking forward. This is still, the paper should be out, right?
The paper should be out.
Okay,
by the way, this is work done by my master student Aurélien Dercy in his master project 2 years ago. Then he worked in finance for a year, and now he's doing his PhD at Harvard, and he's very busy. And but we will finish it. We will finish it hopefully soon.
Great.
And Andrea as well. Andrea now is at Imperial College, but we want to finish it. And by the way, a lot of the work that I described today was not only done with these two guys. It's based on work I did with Ira Rothstein, Walter Goldberger, and Solomon Endlich 6 years ago. Work that eventually didn't go anywhere because we were not sure of what we were doing. I gave a talk, if you remember, 6 years ago at Weizmann. You probably forgot, Marco.
I remember.
Simeon gave his great talk on
no, I remember. When Simeon was talking about large charge, the first paper, the first talk on large charge. Yes. No, I remember his talk, not yours. So that's a bit sorry.
Yeah, okay, it's fine. Sorry.
Sorry.
I also remember his talk better than mine, honestly. Okay. So that was also done with them, and it's not clear now. Even authorship is not clear. Okay, I'm giving a talk at Carnegie Mellon next week. We'll see. Okay. I'll be very happy to have all of them together, of course. The only thing is that Aurélien and Andrea have really worked a lot on this in the last 2 years.
That's
all this part was done by them. But I think Walter had already started doing this 6 years ago. And then probably for some reason, we decided, I don't know, I have to ask Walter. Anyway, good.
Okay. Well, very nice having you. And well, okay, the ones that remain, I'll see in 2 weeks for the next seminar.
Before I disconnect, Simeon.
So,
Simeon, do you want to chat briefly later, or should I just send you an email? I completely forgot to answer you.
Oh, whatever you'd like. I'm sorry. I wasn't. By the way, I didn't show up at your seminar to bug you.
No. But I realized. I mean, I forget things. So anyway, we can talk very briefly on Skype, or I can answer to you by email. I can answer to by email, right?
Whichever is more convenient for you. I mean,
I will send you a message right away. Okay, very good.
Okay. But this was a great talk, and it's really fascinating. So
I think it's fun. As you see, I cannot answer to 95% of the questions, but that's why it's interesting.
It's an interesting idea, and it looks, amazing.
It's crazy. It's different. Maybe it's totally relevant. As I said, maybe this is truly onanistic, but well, why not? Okay, why not?
Yes.
Good.
It looks great.
Thanks, Riccardo.
Thank you.
Ciao. Bye.